Hello everybody. In this video we will discuss base catalyzed hydrolysis of esters. So previously we have talked about acid catalyzed. So if you haven't watched that video, so make sure you watch that video first, or this one, whichever you prefer. So this one is a little bit easier mechanisms than the acid catalyzed one. So let's see what exactly is happening here. So we have a nucleophiles that loves positive centers, right? So can you identify where there is a positive center in this molecule? Well, we know that the carbonyl carbon here, the carbon has delta positive charge. So our carbon here is a electrophile. So here the carbon is an electrophile. It has delta positive charge. So it has delta positive, and oxygen obviously has delta negative. So carbon is an electrophile. So this is an electrophile. So this is exactly what you have to do every time you do any organic chemistry. Just identify positive centers and identify negative center. In this case, this is gonna be your nucleophile. It loves positive. Okay, so what would happen? So you have negative and you have positive, so obviously they're gonna attack, right? So I'm gonna delete this arrow to make it a little bit cleaner. So here, so this would come and attack. When it does, if nothing changes, you will see carbon has 1, 2, 3, 4, and if you have another one here, OH, then it has 5 bonds. To maintain the octet, the pi electron has to move up. So now, okay, I will draw the lone pairs here as well. So now what would happen is you will have a situations that's gonna be like this: OCH3, and you just added OH. Okay, so this is tetrahedral intermediate. So this carbon atom is now sp3 hybridized carbon atom. Before it was sp2 hybridized carbon atoms. So going from sp2 to sp3, it becomes tetrahedral. So this is our tetrahedral intermediate. So we have talked about this before as well in our previous videos, that tetrahedral intermediate with O negative charge is unstable. Tetrahedral intermediate with O negative charge is unstable, and it wants to remove a group so that it will go back to its glory days of sp2 hybridized carbon atom. So in this case, we have a couple of choices. I could bring this negative charge back, so I could bring those electrons. So it has negative charge. So I can bring back my negative charge here, and I could remove a group. So obviously you cannot kick out CH3. So you cannot kick out R minus. These are very, very strong base. So you will never kick out anything that is CH3, which is in general when we say R, that's the group of R, right? Or you cannot kick out H. So these are very strong base, CH3 minus or H minus. So you cannot kick them out. So that leaves us two choices. You can kick out OH or OCH3. So which one is better? So as we know that pKa of alcohol and water, there's minor difference, but they're almost around the same. So the tendency to go out is almost equal. So you can, alcohol is in general slightly weaker acid, but the pKa value of water or alcohol is almost same. So the propensity that either one of them can go out almost equal. So as a result, let's say this molecule goes out. So if this thing goes out, that's basically going backward, right? So this reaction, the first step of the reaction is going to be in equilibrium, because the OH could technically fall off and you're basically revert back to its original. However, let's make something different. So let's say we kick out this particular group. So what would happen once that reaction happens? So how does it looks like? So our product here is gonna be CH3 CO, and I will have the green OH. Okay, I will show this here, OH, and maybe I wanna show the lone pairs. It's not relevant, but just in case. And then what is the other product? Byproduct is gonna be CH3 O minus. That just left the reactions, right? CH3O minus. And you notice CH3O minus is a very strong base. So CH3O minus is a very strong. So this is pretty strong base, just like you have OH minus. And what you see here, we just made a carboxylic acid. Carboxylic acid. So obviously this is an acid and this is an base. So what happened when you have acid and base? You're going to neutralize it. So there is acidic proton. So this is our acidic proton. So what happened? So you have a base and you have acidic proton. So they will neutralize each other's to make alcohol and carboxylate ions. So again, it doesn't have to be CH3O minus, it could be another OH minus. But remember, this is base catalyzed reactions where you have ton of OH minus, a lot of OH minus in your reaction. So it will basically get neutralized. So you have excess, so pH is higher, and you cannot have acidic proton when you pH is higher than 7. So here you'll immediately neutralize it. So the product that you will be making is CS3 CO O minus O minus. So that's your carboxylate group or acetate. Okay, so that's your acetate, and the byproduct is CH3OH, alcohol. So this is an alcohol, and this is your carboxylate ion. So in general, you will see, obviously you cannot have hydroxide ion on its own, right? So let's say you're doing base catalyzed reactions, either you will add sodium hydroxide or potassium hydroxide. So there will be a sodium plus ions. So then when you do all this reaction, eventually the counter ion for your acetate will be sodium. So if it's sodium hydroxide you used in the beginning, you're gonna get sodium acetate. If you use potassium hydroxide, then you get potassium acetate. So that will be counter ion for salt formations. So again, the acid react with the base. So this is an acid react with a base to give you salt and neutral product. Okay, so that's our base catalyzed. So let's do one more problem. What would happen if we have a cyclic esters? So we have this, and we have base catalyzed. So what would happen? The same way. So this would attack on the carbonyl carbon. So this would go up. So you will have a situations where you're gonna have O minus, and we will have OH. Okay, I will color code again, OH minus, and then it wants to go back to its chloride. So this is your tetrahedral intermediate. So that's your tetrahedral intermediate. And tetrahedral intermediate with O negative wants to collapse back. So it wants to bring back. Obviously, you cannot kick out a carbon chain. It has to be either one of these two. So again, anything is possible, equal propensity. So if this thing goes out, then you're gonna go backward. So let's make something different. So let's bring this and bring this one out. So what did we make here? We're gonna be making COOH. Oh mine. Oh no, I missed a carbon atom right there. Okay, so we're gonna get O minus. Now this O minus would abstract the acidic proton here. So this is OH, right? So this O minus would abstract the acidic proton to make your O minus, and there will be an H here. I'm just drawing them before OH. Okay, so I'm gonna draw this in a little bit prettier way. So let's number them. This is your first carbon atom, 2, 3, 4, 5 carbon atoms. So we got it, 1, 2, 3, 4, 5 carbon atoms. So we got our O negative. So you can see here, that's our green O negative. This is 1, 2, 3, 4, 5 carbon atoms, and the fifth carbon atom is connected to oxygens, right? So that's your O and H. So the reason it's get deprotonated because pKa of alcohol is close to 16 and pKa of carboxylate is close to 4. So the reaction always favors the weaker acid. Okay, so that's the base catalyzed hydrolysis of esters. Let's stop here.